that a region where electric potential is constant, what will be the electric field in that region?
It is necessary that electric field will be zero in that region.
Yes, it is zero there. Means simple answer to that one. Someone is drawing like say lines in the notes and say that these lines are actually equipotential surfaces. I don't know whether they can be line, can be a surface. Line is line. So if they are surfaces, then they will be called equipotential surfaces. Then in this direction, it is, you can say the electric field is non-zero, while in this direction it is zero, or some, for example, logic is given there. That's completely wrong. Wherever the electric field will be, the potential will be constant, the electric field will be equal to zero. Electric field is the variation of that potential. Okay. Now, so first understand a little bit this potential, that what a potential means. You know about gravitational potential. You know about gravitational potential energy. Now, how I can say that it is not necessary that all vector fields will have scalar potential, right? Not all vector fields are having scalar potential. Like electric field is a vector field, but its potential is a scalar potential. Magnetic field is a vector field, but its potential is not a scalar potential, right? So what we say? We say those vector fields which are having scalar potentials are actually called conservative fields, right? Those fields which are having scalar potential, which are having associated scalar potentials, will be conservative field. Their del cross means their curl will be equal to zero. They are called conservative fields. Clear? Del cross B is never zero. You can't make it zero. But del cross C is zero. So, the gravitational potential, I can say that it is the gravity per unit mass, right? It is the gravitational force on a unit mass. Similarly, electric field, it is the force on a unit charge. So there will be, first there will be source. That source will have some potential. That potential will cause, the variation of that potential will cause a field, and that field will cause a force, right? Source, it will have potential, variation of that potential will be field, that field will cause force. So we say that electric field is the variation of electric potential. This potential is scalar in nature. So now you know about the absolute electric potential and you know about the potential difference. They are different things. Electric potential or absolute potential is not something measurable. It is absolute. Absolute means it is not measurable. Okay? It is not a physical quantity. While potential difference is a measurable thing and it is a physical quantity. Clear? Electric potential, which you call the absolute potential, is not a measurable thing. Why? Because in the definition you say you are bringing charge from that point where you have no potential, zero potential. That point principally is infinity. So who will define that infinity? How you will measure it? It's not possible. But potential difference is between two defined potential, there is a difference. So it is measurable thing. Potential difference is a measurable thing, while electric potential is not a measurable thing. Right? So you should understand this attitude, this behavior. And further, electric field is the variation of that potential. If potential will not be varying, electric field will be equal to zero. Like this is a surface, and this surface is having constant potential all over the surface. So on this surface, the electric field will be equal to zero. This surface you call equipotential surface. Everywhere the potential is the same, while electric field is the variation in this potential. Clear? So the electric field will remain zero on this surface. If you consider a conductor, then on a conductor, along the whole wire, it is equipotential. So along the surface of that whole conductor, electric field is equal to zero. Right? Clear? So with this preface, we will now start with some derivations of it, and we wrote that F is equal to K Q Qi and X minus Xi divided by X minus Xi cubed. And the work done to bring the test charge from infinity to some observation point X, this work is equal minus from infinity to some observation point X. Why I am writing minus? Because I am doing work against the field. I am bringing a charge from somewhere where the potential was zero to some potential. When the field will be doing work, when the source charge will be doing work, it will be a positive work. If I will be doing that work, it will be against the potential and it will be minus. So this is equal. Now the work, you know that it is fx prime dot dx, or you say that this is ds if you like. This is, in order to differentiate with x, you say this is ds, where ds will be that length element through which you would have applied this force, and this much work would have been done. So I can write now the force in this form is minus q integral from infinity to any observation point x and e at x prime dot ds. Clear? Where ds is the displacement along some path. So this work integral is simple in coordinate system relative to xi and the origin. So let me plot this one as well. That let's say your qi is here, your qi is here, and the position here is xi, and from this point to this point you are having x minus xi. This is the same as we did earlier, and from here let's say you are bringing it like like this way. So this point, consider this point is x prime minus xi, and this is, let's say, the length element ds. Just bringing that one from, this will be your, let's say, infinity region. So I can write that W is equal to minus q from infinity to any point x, which is the observation point, k qi, means I am now writing that in this form, x prime minus xi. You will now have to keep in mind that what was x and what was xi, and x prime minus xi cubed. Xi is always the distance of the source point from the reference point, while x is from the source point any distance, dot ds. So I can write that if I write this r, which is x prime minus xi, this one is absolute and this one is absolute. This one is absolute and this one is absolute. Means x prime minus xi is equal to r. Then I can write the work will be equal minus q from infinity to x minus xi k qi dr over r squared. Means just converting x prime minus x, this is our r. So our this one from the vector form, you convert it into a scalar. So it is 1 over r square dr, just like you are writing the electric field, 1 over r square r. And now it will be from infinity to this point, from the reference. So because it was earlier any x point, and now our specific x minus xi. So I can write that this is equal, this work is equal to, what will be this, minus 1 over r, and then put the value this one. So you will have q, this q, and k qi, and 1 over x minus xi absolute. So the electrostatic potential at position x due to qi. Now if I move this one here, means work done on a unit charge, then it will be defined as phi of x is equal to work done on a unit charge. This was our test charge actually, which we were bringing, and this will be equal to k qi divided by x minus xi. Alright, you write this one, that this will be the, let's say, for a ith charge. Then for the total charges, if there will be many charges, then for the total charges, I will write that total potential will be the sum of all of them, means summation on I and k qi divided by x minus xi. or I can write this thing is, if I want to write this in integral form, summation this one goes to integral, then Qi will no more be discrete, but this will become the charge density, and this will be equal to K rho x prime dq x prime divided by x minus x prime, and this will be the electric potential at point x for a collection of charges. Similarly, we know that force is equal to the negative gradient of work, right? The negative gradient of work or energy. You say potential energy or what energy you like, and then you know that if I write this thing, if I divide this side on Q and I divide this side on Q, because it's a scalar. Now this F over Q I call the electric field, and this is the minus gradient, and W over Q from here is actually the potential. So I can write that the electric field at X is minus gradient of phi X. So the negative gradient of potential is called the electric field. I can further, means to understand this in one dimension, then I will say that Ex will be equal to minus d phi over dx. If phi will be constant, means the potential will be constant, then the electric field will be equal to 0.
Phi is constant. Anywhere it is constant,
Then the potential electric field will be equal to 0.
okay, and the same few differences about this one. Just in 2 minutes we will discuss this one. I have told you earlier as well, but just clarify this conceptual issues.
If you are having a positive charge, then this positive charge will have some electric field at a certain point and some potential as well. Means both this one will not be equal to 0 and V will not be equal to 0. If it's a positive charge, it's a negative charge. Irrespective of that, it will have some electric field, it will have some potential. Clear? Now where the situation becomes complex, that if you are having a positive charge and here you are having another positive charge, then positive charge is there, source is there, so it should have electric field. Here is a positive charge and it should have electric field. What about the electric field exactly at the center? The electric field is 0 at the center. Now, if there will be no charge, like the electric field is depending on the source charge here, Q. If there will be no Q, electric field is 0. And there are Q's and electric field is 0. Right? So how to differentiate between these two zeros? One zero is due to magnitude, is due to the source charge, while the other zero, this zero, is not due to the source charge but due to the geometry. So the vectorial nature of E actually fits here and it gives you 0 result. So for the mathematics to differentiate between this 0 and the magnitude 0, you define potential, and certainly that quantity is non-zero here, right? Means this one fails due to the geometry of the charges. So this one is non-zero there, right? But non-zero can be, then from this definition, you say that electric field is the negative gradient of this potential. I'm writing V here, you can write both the forms, with V or phi. Now V is non-zero. If V is non-zero, then how this one can be zero? So the only possible way is if the variation in this one in space is equal to zero. If it's a constant, if it's constant, then its derivative, space derivative will be equal to zero. And that's the reason that whenever you say the equipotential surfaces, so from equipotential surfaces, your electric field will be zero on those surfaces because potential is not varying there. The variation of potential is called electric field. Now consider two other charges, positive and negative. What's about the electric field here at the center? Non-zero. What's about potential? Potential is zero there, right? But electric field is non-zero there. So now you are having two things with you, so the geometry will not be deceiving you. Clear? Okay, thank you.